fraction population that will be the half, the width at the half height. Variance and standard deviation are related to biosquare. So these are things that you probably have learned before. Why do we want to know the variance or the standard deviation? That's because for one reason that if you know how variance is related to each other inside a map, then you can tell that these two things move together. So they would, I should say, they fluctuate in the same way. Most likely they will move together. The other thing that you can use this information for is simply to gain confidence of your difference map. In other words, that what is being called the t-test, that's been, you probably have used this before for some biological measurement. T-test mainly is that it's a standard error weighted differences. So that's, if the error, the standard error, which is, for the mean, is calculated from the standard deviation of each of the population you are trying to, each of the measurements that you are calculating. So that standard error value gives you a weighting in such a way that if both of those numbers are not very certain, then your T-map will come out to be a smaller number. So if each of them are very certain, in other words, these peaks are sharper, then for the same amount of separation, same amount of differences, you actually will get a bigger value in the T statistics. So that gives you a better way of describing your differences. So what's the bootstrap resampling? Purpose of that is trying to figure out what that variance or the standard deviation is of your measurement. Although the ultimate goal is of what you want to know about what's in the distribution. So, for example, here you have a population distribution look like this. I mean, it's showing it as different colored balls, so each has the different values. You are making a measurement, meaning that you're making a number of measurements. It means that you are drawing samples from this population. So, say for example, I draw seven times from this population, and I end up with the sampling population distribution like this. And then you want to calculate a quantity out of it. Now, the most common example is to try to calculate the mean value. Then you will take this and then you add them up divided by the number of measurements. So you end up with some quantity, some result. So what we are trying to estimate is the distribution of that quantity to find out what's its variance if we have done this measurement many, many times. In other words, if I'm actually doing this with the whole population, what will be the distribution here? Okay, that's the ultimate goal. In general, that's not a very easy thing to do because you probably only did this 7 times. If we are talking about our 3D volumes, it's good enough when you get one map, not to mention that you try to get a meaning of that then in order to get the population, the real population. So you end up having to estimate. So bootstrap resampling method is a very good way of doing this. It's a Monte Carlo method. In other words, you can just do it over and over again, and just by you can say by chance or by the way it's distributed, then you'll be able to get the answer. So the way it's done is like this. You take your 7 samples or your 7 measurements. Imagine that you put that into a box, and then you just blindly go in there, randomly draw a sample out of it. That's as your first resample. And then you put that ball back. in order to not to disturb your distribution, is so-called the sampling without sampling with replacement. So you put it back, and then you take another one out. It's not necessarily the same one or a different one. And in some cases, you may draw out the same one. That all depends on the population distribution inside that box, your sampling distribution inside that box. So I do that to the same number of the samples I had at the beginning. Now I end up with seven values. They are not really new, but they may distribute slightly differently, just because that you didn't know which one you take out. Now, use these 7 numbers, then you can recalculate the quantity that you are interested in. Then you get a value out, because no matter how, how you get this quantity out, no matter how complicated, like our reconstruction, we take images and then we try to get the reconstruction. The process is very complicated, but we know how to do that because we've already done it once. So we can do the same thing with this. So now you get one data. This is not going to be the same as that. It's going to be a little different because the way this is drawn is different. Now you repeat this process again and again. Each time you will get slightly different results until you create a distribution of this new resampling. So you can do it many times. Eventually, you are going to create a distribution that is now from the bootstrap. The way the theory goes, that you can use that to get the population, to get the distribution of the original measurement, the quantity that you can derive out of your original measurements. So here is this how it's stated. The standard deviation of this bootstrap distribution is equal to the estimate of a standard error of the quantity you are interested in. Okay, so this was developed like in 1979. It has a lot of applications in many different fields. So it's pretty powerful, but also a bit dangerous because it's too easy to do. So a lot of people abuse the method. So I certainly then, what I wanted to do was to try out first to make sure that we can actually do this on 2D crystals. So the first thing I did was do a simulation. I created a simulated crystal, with 2 lobe of density, and one of them stays constant, and the other one flipping it into 2 different conformations. Just randomly put that into a 200, I think it's a 40 by 40 or 200 by 200 lattice, and then pretending that's a crystal that I got from the microscope, and I can calculate the projection map out of it. Doing the same thing, go to Fourier space, get amplitude interfaces. Then when you can do that, if I know how to do that, then I can redo this process again every time I randomly draw my new crystal. So each one of my the images are different. So I have a number of them. I think I had 64 of this kind of images. And then I can start doing bootstrap resampling to see if I can get a same estimation of the variance back, because I knew what my variance is. So the result was pretty satisfactory. That this method does work for 2D crystals. The kind of a process that we went through, we've been able to retain the shape of this variance map. Now, of course, I didn't do this for fun. I actually didn't like statistics when I was learning it, and the reason I ended up doing this is because I ran into a problem with the project. At the time, I was working on gap junction channel protein. The the goal of the project was to look at the differences between the wild type 43 connexin and its C-terminal truncated form. The C-terminus is 15 kilodalton. The whole thing is 43 kilodalton. I should be able to see a big ball in the external domain. This other part, there are 4 transmembrane helixes. So I got 2 maps. Of the 2, they look pretty much the same. So I've been wondering, what am I going to do with this? I can see from my lattice line there are some small differences, but they are not big enough to account for the whole mass. So there are some other things that changed, despite the fact that I cannot see the C-terminus in the map. So the reason I want to show you this is because there are some tasks that I end up doing in the 3D that uses a certain property of this particular protein. The gap junction structure now is made out of a 12 connexin protein, and it's 2 hexamers docked end to end to each other. So here's the transmembrane part, the 2 transmembrane domain, and there's the extracellular gap, which form a really tight seal. So it is a good channel in between 2 cells. This crystal is in P6 symmetry. The molecule, however, because the way the 2 hexamers are docked together, it has a pseudo 622 point group symmetry in there. So I can use this property to test certain things about my algorithm, see if it works in 3D. So what I did was that I take one of my map, I mirrored it, and then I merge the 2 mirrored map together. This way I produce something that it would have a mirror symmetry. So this is the 2 map. This is the merge map, and I'm showing here in order to show you the mirror symmetry. So it has a non-crystallographic mirror symmetry in there because of the way my protein looks like. While I'm doing all this bootstrap resampling to estimate my variance, or when I'm calculating density, it never actually used this symmetry. So my expectation is that if I'm doing this right, when I finish my bootstrap resampling, my variance map should have the same kind of symmetry. So indeed, once I get it out, it does have the same symmetry. So and also the location of the major peak corresponds to the major differences between the 2 mirrored maps. So that confirms that this method works. So with that, then I actually calculate the variance. Now remember, the purpose of this for me was in order to be more confident with my difference map. So I need to get my variance map. And the result looks like this. If you look from the top, there are certain peaks. There are not a lot of them are very strong. The strongest one is, of course, at the 6-4-fold or 3-fold axis. And that's expected because in those places that you don't have a symmetrical mate to average, so your error there is whatever number of times larger of your rotation symmetry. The other thing that we found we found out that there are more variance in the extracellular domain surrounding this area, just slightly more than all the other places. The last thing we noticed is that I had the two forms. I have a truncated form and I had a wild type. The truncated form has bigger variance than a wild type. And that's very reassuring because it's interesting that the wild type crystals, they are small, they're really hard to find. But when you find them, they are perfect hexagon. In other words, they are really single crystals. On the other hand, the truncated form, because the way we treat it, probably that they are larger, but they in general are not a single crystal looking thing. So once I have variance, I can calculate the T-map, and this is a T-map. I'm not going to go through that much of details on this. All I can say is that it turned out very similar to the difference map because they really, as I said, the variance map wasn't. I didn't see a very strong region that has a very large variance. So that's the end of the exercise. At the end, that I could identify regions that had more changes than others that I'm more comfortable with. Now, to the update, since then, I think in 2008, that there was a connexin 26 crystal structure came out of this type of protein. When I duck that into here, then I can find out, exactly which transmembrane helix is that's, all those changes that I observe here. From what the differences here, you can say that okay, here is the helix that's closer to the pore is doing some sort of a rotation and a movement. It turns out it's the first transmembrane helix, so that has nothing to do with my C terminus. So up to date, I still can't publish this. It probably will never be published because I really can't find, even though I find a statistical significance in it, I don't find any biological significance for what I've observed here. So in a way, that even though the method is a success, that the project is a failure. Okay, so what I want to show you here are several methods that has been tried, and I think it was unsuccessful. So if you ever need to do this, you probably shouldn't try them again. Okay, number one is that if you do have an image that you can reconstruct your 3D map directly from that one image, you can calculate this variance from just the typical method. This can be done in helical reconstruction, and obviously you cannot do that with 2D crystals. The second method that has been tried is do a reconstruction looking at the differences, using the differences between neighboring orientation. So this is done in single particle field where they have many, many different orientations. So their neighbors are very close to each other. So when you look at that difference, you can sort of make the assumption that this is just a statistical differences between the two. That was tried as well. The result wasn't very good. I think one of the problems is that that assumption of that you and your neighbors are only different by your statistical variation, it's not quite right, because we know when we're doing classification, we intend to have them look a little different from one class to the other. So that didn't work out very well. And of course, we cannot apply that to 3D crystal because our neighbors are very far apart from each other in a 3D space in terms of altimeter distribution. The third one was done earlier. That basically the idea was a naive one. You thought that no, we can do this, so we can vary the amplitude and the phases in the Fourier space, And for each of the variation that you create, then you can reconstruct the map and use those maps to estimate the variance. That really doesn't work, and it shouldn't work, because when you are doing things in Fourier space and when you translate it into real space, the distribution really the distribution it will get distorted, and so I tried this, and then I realized that it caused distortion. So I knew that it would not work. So that's something you should not try. There's a last method. This is also a very well-established method in statistics called the jackknife estimation. The idea there is a pretty simple one. You have your measurement, you have a number of measurements. You take one measurement out. You calculate your quantity. Then you do another one. You just take one out. So each time you have one less measurement in there, and then you can use the whole thing together. It's called jackknife because the person invented it thinks that everybody should have one. And I tried that. The result wasn't as good as a bootstrap. So that's something to know. So while I was compensated is that the Pavel was so we know that there's also methods developed by Pavel Pensek in single particle. I'll tell you the history of this. So I'm going to make a comparison here that how it applies in 2D crystal and in single particle. For when we are doing this 2D crystallography, the sampling unit is each of the large of crystal image. When they are doing it in single particle averaging, they will use each of the box particle. The number of samples for us is from the 40 to hundreds. No, it's not a very large number. For them, they are going to go thousands to a million. So it's a very different scale in number. The number orientation for us will only still be in hundreds, at the most in hundreds. For them, that it will be the same as the number of classes that you are trying to you use that for your classifications. So that can be a reasonable large number too. The required number for resampling. At the time that we were about to publish the results, we each did some estimation, and Pavel came out about 400 is good, and I agree with him. So we just did 400, and but since then he has a paper came out in 2008. In which that he estimated what he needs for getting results, a good what considered as a good estimate for 21,000 particles. He ended up doing a lot more cycles. The rationale there is that he gathered that what we are looking for is not just the confidence value here. As you go up in number of bootstrap cycle sampling, the differences between one cycle and the previous cycle can be estimated in a way of looking at the differences between different pixels. And he did a series of simulation and derivation, and decided that you should use it when that is minimized, not just the amount, the variation overall. So the last is how much of a single processor time needs. Because of the number of images that we have is very small, so we typically don't take as long. And the last, there are a lot of publications you're going to see nowadays about using this method to do so-called focused classification. In other words, using that variance and the covariance information to mask out regions that doesn't change. Then you've been able to classify different conformations within the range of where you have the biggest variance. This, unfortunately, probably won't work in 2D crystallography because the overlapping of the density in the crystal. But there's still a possibility that you can use it, so you should keep that in mind. So in conclusion, the method yielded a good estimate of the standard error of your reconstruction. And once I calculated out, it's as expected, it's dominated by the artifact at the symmetry axis. And the third is that the variances that I got for the gap junction is the largest at the boundary of the pore with some other different location. So here are the 3 references of the original publications. And I'd like to thank Mark Yeager. I was working on this project for, I don't know, for a long time. And this statistics excursion would not have happened if we decided that we just drop this and just say nothing happened to the project. I want to thank Pavel. I got the idea of a bootstrap when he gave a talk at Biophysical Society. That's before his publication, and it's just at the time I ran out of idea. It certainly was what really worked for this case, and we had a very good discussions, and he even let me read his manuscripts before publication. So that's really helped this project. And in addition, I would thank other people. June helped me for a lot of simulations. And Carolyn Danigan is a statistician at Scripps. She's the only one locally who can actually, when I say bootstrap, she will come back with, why didn't you use jackknife? So really thanks for the discussion that we have. So that's it. Any questions? Depends on the purpose. I mean, if you want to know the variations within your image, your crystal image, then that would be what you do. As far as the quantity we are measuring, at the moment, is a combination of all the different crystals that we have. It's not just things in that image. By the time we extract all the amplitudes and the phases, we already did the averaging inside of the crystal. So your distribution is already being affected by the variation inside the crystal. So in other words, that divided it up, it's not going to help you in overall goal, but it will help if you are interested in variation inside of the crystal. That makes sense?